Good evening, everyone. We're delighted to be joining you again from the Kavli Institute for Particle Astrophysics and Cosmology here at Stanford University, as we continue our series of presentations inviting you to discover our universe. My name's Dan Wilkins. I'm a research scientist at kipac and the coordinator for our public talk series. And don't forget, you can find out all about our upcoming events over on our website, kipac.stanford.edu/discover. And you can watch any of our past talks again on the website or on our YouTube channel, or you can sign up for our mailing list to make sure you're always up to date with what's going on at kipac. This evening, we're joined by Dr. Chia-Hsun Albert Chuang. Albert is a research scientist here at kipac, and he received his PhD from the University of Oklahoma in 2011. Following postdoctoral research positions in both Spain and Germany, he came to Stanford in 2017. And he's now the co-chair of DESI Simulation Working Group, and he's working to prepare the computer simulations of our universe and the data analysis pipelines that will allow the DESI team to translate the maps of the galaxies that Albert's going to tell us about tonight into an understanding of how our universe is put together and how our universe is expanding.
Thank you, Dan. Let me share my screen. Does this look okay?
Yeah, looks good.
Okay, great. Hello, everyone. Do you know our universe is expanding? It is getting bigger and bigger. How do we know that? How to measure the speed of the expansion of our universe? My name is Chia-Hsun Chuang. I'm a research scientist working at Kavli Institute for Particle Astrophysics and Cosmology. Today, I will explain an ongoing project which is using a very powerful telescope to measure the expansion history of our universe. First, I would like to say kipac is a joint institute of Stanford University and SLAC Laboratory. Stanford University has a beautiful campus, but I'm sorry that I cannot invite you to visit at this moment due to the pandemic. SLAC is a national lab, so that you do need a permission to enter no matter what. Today, even I cannot get permission easily since most of my work can be done remotely. In any case, we have not stopped our work on research at all. What I'm working on is cosmology. We are trying to answer some basic questions, such as, what do we have in our universe? How big is our universe? How old is our universe? What is the temperature of our universe? Have you ever thought about these questions? So how do we learn about our universe? We look at the sky. We also do experiments in the laboratories on Earth, but let's focus on sky today. On a clear night, from a dark location, you can see thousands of stars with your naked eyes. Basically, the stars we see are in our Milky Way galaxy. Our sun is just one star among roughly 100 billion stars in the Milky Way galaxy. Sun is about 25,000 light years from the center of the Milky Way galaxy. In fact, we can see not only the stars in our Milky Way galaxy, but also the stars from other galaxies. However, in the case of looking at the other galaxies, we do not see individual stars. We see a whole galaxy as one object. By eye, it is difficult to tell whether it is a star or a galaxy. If it is a galaxy, we are actually looking at the lights from billions of stars together. Let's try to zoom in, say, this area. We can zoom in with a telescope. This picture was taken by the Hubble telescope with 21 days of exposure time. Hubble telescope is a space telescope. It can point to one direction to observe without interruption, unless the area goes behind the sun. It is different from a ground telescope that we cannot see anything during the daytime. As you can see, some of the object has shapes. These are clearly galaxies. However, for the point-like objects, they could be stars in our Milky Way galaxy, or they could be galaxies far, far away. How can we tell? We can learn much more about this object by studying their colors. We will be able to tell whether they are stars or galaxies. The white line here shows the light beam from a star or a galaxy. When it goes through this triangle glass, the light reflects, which means it's changed the direction. If you put a pen in a cup of water like this, you can see that the pen bent. It's because the light reflects. Also, different colors reflect with different angles. So in the end, they separate. This is the same reason that how the rainbow forms. Of course, there's no triangle-shaped glass in the sky. The lights from our sun are reflected by the little water drop in the sky. This is why the rainbow usually shows up right after the rains. By the way, I want to mention some terms here. This triangle glass called prism. And the whole device, including prism, detector, is called spectroscopy. Based on this very fine measurement, using a very fine measurement of color using spectroscopy, we can find out many things about the galaxy or stars. What can we learn from these colors? The plot here shows the colors we measure from one object. As you can see, we have separated the colors using spectroscopy. Then we measure how strong these colors are. The white curves here shows the brightness of different colors from this object. The lines here are showing some specific colors from this object. By eye, we cannot tell is this color this red or this red or this red. They are all red. We cannot really tell the difference. But with spectroscopy, we can determine how red the object has and how bright it is. Once we have the detailed colors, we can determine whether this object is a star or galaxy. If it is a galaxy, we can also determine the distance between the galaxy and the Earth. We can also determine the moving speed of the galaxies. These are very important information for understanding our universe. So here I'm going to talk about how to measure speed and the distance. How to measure the speed of a galaxy? We make use of Doppler effect. What is Doppler effect? Actually, you might hear it every day. When an emergency car approaching, you will hear a high-pitched siren. When it is moving away, you will hear a low-pitched siren. As shown in this car, if you are standing in front of the car, then the sound waves are denser, so that you hear a higher pitched sound. If you are standing behind the car, the sound wave would be more sparse, so you hear a lower pitched sound. This is called Doppler effect. The frequency of the sound is related to the speed of the object. The same thing happens to the light waves. If the galaxy is moving toward us, then the frequency will be higher. So we see the light will be more blue. If the galaxy is moving away from us, then the frequency will be lower. So we will see the color become more red. So if the light becomes more red, it is called redshift. It means the color is shifted to red. If there are some spatial lines from this object, we will see these lines shift to red side, which means that it's moving away from us. How much redshift is determined by the speed of the object moving away from us. In 1929, Hubble found that more distant galaxies were moving faster away from us. The speed of the galaxy moving away from us is proportional to the distance between the galaxy and us. As you can see, the x-axis here is the distance of a galaxy from us, and the y-axis here is the speed of the galaxy moving away from us. Velocity also means speed, and we can also use redshift. We use redshift to measure the speed. And it turns out that the relation between the speed and the distance is a straight line. And this plot is the data that Hubble actually used. Hubble, I mentioned his name a few slides ago. Yes, the Hubble telescope is named after him, but I don't think he has anything to do with the design or plan of this telescope. We named the telescope after him to recognize his contribution in astronomy and cosmology. So his discovery, Hubble's law, implied that the universe is expanding. Okay, here is the idea. Every place in the universe looks like every other place. The Bay Area is not the center of the Earth. The Earth is not the center of the solar system. The solar system is not the center of the Milky Way. The Milky Way should not be the center of the universe. There's just space with many galaxies. If the whole universe is expanding, then the nearby galaxy would be moving slower away from us, and the distant galaxy would be moving faster. Like if you look at the two galaxies nearby, then the velocity between these two will be slower. If you look at the galaxy far away from each other, then they will move faster from each other. And this is what Hubble discovered. So we know our universe is expanding, but we want to know more. To know more, we need more data. At the time of Hubble, they measured the colors of galaxies one by one, but we can do much better now. Here is a way to collect light from many galaxies at once. First, we take a photo with a telescope. And then the circle on the left picture shows the area observed by the telescope. Then we prepare a plate made of metal. Okay, on the picture on the right. Once we decide which object we want to measure the color, we drill a hole on this plate, matching the position of those objects. We then replace the camera in the telescope with this plate. Usually we put camera in the telescope to take pictures, but now we replace it with this plate and then point the telescope to the same direction that we took the picture. So the lights from different galaxies or stars will go into different holes. Behind each hole, we prepare a fiber to collect and direct the lights to the device which we measure the colors. If you remember, the device measure the colors is called spectroscopy. This video is showing how we plug the fibers in the holes to collect the light. The light comes from the other side of the plate and is spectroscopy to measure the color of light. This metal plate and all the fibers will be put in the telescope once they are ready. I'm going to show you another video. This video shows the daily routine, how we use Sloan telescope to collect the color of galaxies. The project is called Sloan Digital Sky Survey. It can measure the colors of 1,000 targets at the same time. Before the sunset, we take the plate with 1,000 fibers from the storage place and then bring it to the telescope. We replace the old plate with the new plate. So the old plate is taken off. Now the new plate is put on. We put the old plate back to the storage place. The size of the mirror of this telescope is 2.5 meters. This project scans 1/4 of sky. The telescope is located at Apache Point Observatory in southeast New Mexico. At night, Once the telescope starts to observe, it takes about 20 minutes to collect enough lights from the 1,000 targets. Then we will replace the plate again to observe another 1,000 targets. Here you go. They are replacing the plate. We have collected data from 2.5 million galaxies, which means that we have used at least 2,500 plates. Remember, we can determine the distance between a galaxy and us based on the color of the galaxies. After collecting this data, instead of making a 2D image of the object in the sky, as typical telescopes do, we can construct a 3D map. In fact, it is more than 3D. The thing is, it takes time for light to travel from galaxy to us. So when we are looking at the galaxy deeper in the sky, we are looking at the galaxy in the earlier time of the universe. So looking at the data from different distance is basically the same as looking at the data from different time. In other words, we are actually seeing the history of our universe. So, as I say, we are not only constructing a 3D map. There is one more dimension, which is time. I will get back to this. After the Sloan telescope, now we have a new and more powerful telescope. This project is called DESI, Dark Energy Spectroscopic Instrument. DESI is going to observe the colors of 35 million galaxies. The left picture is the dome that's protecting the telescope, and the right side picture is the telescope. This is the project I'm working on right now, and let me explain the detail with you with a cool video. Dark Energy Spectroscopic Instrument, we call it DESI, is a ground telescope. It is located in Arizona, nearby Tucson City. This video is for a press release announcing that the telescope is ready to collect the data now. We have some nice cartoon to show how the telescope works. DESI will map 35 million galaxies in 3D, which is about 10 times more galaxies than ever observed, including the Sloan telescope I just mentioned. The light from the stars or galaxies will be reflected by a big mirror. The size of the mirror is 4 meters. Then the light goes through a device called corrector. The corrector is composed of 6 lenses to ensure DESI maintains a wide, highly focused view of the sky. This is the corrector. After passing through the corrector, the light reaches the fiber at the top end of the telescope. Instead of drilling holes on a plate, these 5,000 fibers are carried by 5,000 robotic positioners. As you can see, a thin fiber, the yellow line, is attaching to this pen-like device we call positioner. We can program this positioner to bring the fibers to the right location to collect the lights from the targets we want. The fibers are like 5,000 eyes. They collect the lights from 5,000 galaxies to the 10 spectroscope downstairs. A spectrograph is a device determining the color of the light. So taking this measurement from millions of galaxies will provide a most powerful 3D map ever, which will enhance our understanding of our universe. Besides collecting the data, scientists are also developing theoretical models and making simulations with supercomputers. Once we have the data, we will compare the data with the models or simulations to see how well we understand our universe. In fact, comparing data with theoretical models or making simulations is my main job in DESI. Okay, I would like to mention that it is our honor to conduct research on the Kipac mountain, which is important to the Tohono O'odham nation. So why DESI is called Dark Energy Spectroscopic Instrument? Spectroscopic instrument is saying that this is a device measuring the colors. But what is dark energy? Before answering that question, let me jump to the other topic, supernova. A supernova is the explosion of a star. The brightness of the supernova could be as bright as a galaxy. A galaxy has 100 billion stars. A supernova is so bright that we can see it even if it's far, far away. The picture on the left is a galaxy named M96. The picture on the right, you can see the same galaxy, but there is a supernova nearby. The supernova was observed in 1998. The name of the supernova is SN, means supernova. 1998 means it's observed in 1998. And BU means it's index because there are more than one supernova in that year. And 1998 actually was a very important year for supernova study. I will tell you in a few slides. Type 1a supernova is a type of supernova that would explode under a spatial condition, which make the brightness the same when they explode. Therefore, we can use them as the standard candles, which means that we can tell how far these supernovae are by measuring their brightness. As you can see in the picture, I'm using candles to represent the supernova. The closer the supernova is to the Earth, the brighter it looks. Okay, so this is the brightest because it is closer to the Earth, and it looks fainter because it is far away from Earth, and fainter and fainter. And also, we can measure how fast they move away from us by measuring their color using spectrograph. Remember, we can measure their redshift. Using this information, including distance and speed, we can determine the speed of the expansion of our universe, just like what Hubble did. But we are measuring it in a more precise way, of course. So why supernova 1a explosion have the same brightness? The most likely theory is the following. It starts with a binary star system. One of the stars is a white dwarf, which is a dead star. It burned out of fuel, meaning it does not have enough mass to trigger the next phase of nuclear reaction. It cooled down and that's it. Our sun's future would be a white dwarf. However, the story could be different if there is another star nearby and they are orbiting around each other. If this second star is a massive star, it could lose some gas falling into the white dwarf. So the white dwarf would become heavier and heavier. At some point, the white dwarf collects too much mass and collapse. And that triggers the nuclear reaction and explode. We know how much mass would make it collapse. So even these white dwarfs started with different masses. They will explode when they reach the same mass. That is why all the supernova 1a are similar. Okay, now we know why this type of supernova can be treated as standard candles, meaning that they have the same brightness if you look at them at the same distance. We can use them to measure the expansion of universe. We can even use them to tell the expansion is getting faster or slower. This plot shows the distance based on the measurement of brightness that we call luminosity distance, and the speed of the supernova moving away from us. So now we can not only measure the distance, the expansion rate at this moment, because supernova was so far away, we can measure the expansion rate even a long time ago. Remember, the distance and the time is related. When we look at the distant object, that means that we are looking at the earlier time. So in 1998, based on the supernova data, people found that the expansion of our universe was getting faster and faster. It was a surprise, since in our understanding, the expansion should be slowing down because of gravity. So how is this possible? So one explanation is that there is something else, something we don't know, something that pushing our universe apart. We call it dark energy. The astronomers discovered the accelerating expansion of the universe based on the observation of supernova were awarded Nobel Prize in Physics in 2011. Now you see why I mentioned supernova when I was going to talk about dark energy. So based on this observation, now we know that we are living in a universe whose matter or energy content is dominated by dark energy. 70% of the energy of the universe is contributed by this mysterious force called dark energy, which is causing the expansion of the universe to accelerate. But we do not know how or why. Explaining the nature of dark energy is one of the most important problems in physics. We want to measure dark energy as different way as possible. In physics, sometimes we could develop a theory to explain some observation. To prove a theory is correct, it would be the best if we could have a different independent observation to support that theory. So now I'm going to introduce a different measurement which is not from supernova. To explain that, we need to look at the history of our universe. The picture showing the evolution of our universe. On the left, the universe starts as Big Bang, and on the right, the universe is the universe today. From Big Bang to today, the universe has been expanding. It has been 14 billion years. Today, the universe is super cold and empty, but in the early universe, it was actually very hot and dense. It makes sense because the expansion will make the universe cool and empty. Now, let's look at the early universe when it was hot and dense. At that time, there was no galaxy, no star, no Earth. It was too hot. There was just gas. The gas was composed of particles like proton, neutron, electron, and also light. You might know that an atom of hydrogen is composed of a proton and electron. An atom of helium is composed of 2 protons and 2 neutrons and 2 electrons. Of course, there are other different atoms, but when it was so hot, like 1000 degrees, there was too much energy, so that the structure of atom cannot be held. So it would look like this. In this picture, proton, neutron, electron, all the particles are separate because it was too hot. But remember, this gas was also very dense, so that they were not actually moving freely. All the particles are actually not moving freely. If there was some density fluctuation, it would become sound and spread out. Let's think about how the sound are made. This is a speaker. It vibrates and put pressure on the air nearby. And the air nearby it, the density get higher. The high density air will have larger pressure, and then it pushes the next nearby air. And the next nearby air, also the density get higher, and then it has larger pressure, and then so on and so on. This is how the sound travels. On the other hand, to have sound, there must be something like air, which can carry the pressure and density. So if you go to space, like a Superman, and you talk, even you are a Superman, no one can hear you. Why not? Because the space is empty. There is nothing can carry the sound. However, More precisely speaking, to carry sound, we need the material that hosts the interaction between density and pressure. Let me explain you in these slides. P here is the proton. It has strong interaction with the electron through electric force. And the light here, photon, also has a strong interaction with electrons. The photons move fast, so it provides the pressure. And the proton is heavy, so it provides the density. So the density and the pressure, they talk to each other, or say they interact with each other through electron. So this kind of gas, sound could happen in this kind of gas, or say sound can travel through this kind of gas. I'm writing down an equation here. It just shows saying that you can determine the sound speed if you know the relation between the density and pressure. And we have a name for the sound in the early universe. It's called Baryon acoustic oscillation. Baryon means the particle, including the protons and neutrons, these heavy particles. And acoustic oscillations means sound. However, once the universe cools down, the electrons are bonded with the proton. So the light or photons now is free. So the pressure and the density, they don't talk to each other anymore. They don't interact with each other anymore. So the sound stops. Or we say the sound floats. When the sound wave floats, the sound horizon reaches about 450 million light years. Let me explain you with this plot. If at the early time, for some reason, a location has larger density, it would become a sound and propagate, just like you throw a stone in a lake or pond, and you can see a circle spread out. But at some point, when the universe is not so hot, meaning that the electron and the proton, they form atoms, and then so the sound stops. The ring would not grow anymore. But the density fluctuation at the very beginning of the universe were actually kind of random. It's not like just one point. The density peak actually is everywhere. Okay, I cannot explain why it was random in this talk, but anyway, we have in the initial condition, in the initial time, the density peaks at the beginning were everywhere, and then they all become sound. So the real picture should be more like this. Now you know that there was sound in the early universe, and they stop at some point, also in the early universe. How are we going to measure the BAO, or the sound horizon? Let me bring back this plot, which is the history of our universe. If we look into the space, we can see all the way, here is today. If we look into the space, we can see all the way until the light is blocked. When was that? It was the time that sound floats. Why is that? Remember, the sound floats because the lights were free from the electron. Where is the electron? Electron were got together with the proton and form atom. So since the light were free, they can travel all the way to us, so we can see them. So this is the farthest or deepest place we can see in the sky. There's a name for the light come from this earliest time. It's called cosmic microwave background. Here is the cosmic microwave background we observe from the full sky. Although these signals are light or photons, but they are not visible. Actually, they are microwave. So we use the telescope to detect it and convert it to the color map as shown here. So can you see the BAO or sound horizon here? No, because it looks like a random noise. As I mentioned, the original density peaks were random. So how can we see the BAO? We need some math here. I'm not going to explain the detail, but if you know what is frequency, if you know how to convert the sound wave into different frequency, then I can give you some idea. Basically, we are using the same technique, the same method, but we are converting this two-dimensional density map into the frequency, as shown here. And these peaks are the spatial frequency that which correspond to the sound horizon. This is how we measure the sound horizon, or BAO, from the early universe. Since the sound has been frozen, the sound horizon imprint the universe everywhere after the sound stop. Although the sound stopped, but actually it is still growing when the universe is expanding. So by measuring this BAO, this sound horizon at a different time, remember, it means different distance from us, because it takes time for light to travel. Okay, so we can derive the evolution of the size of our universe. If we can measure the detail of expansion history of our universe, we will be able to explore the nature of dark energy. So since we have already millions of galaxies from Sloan telescope, we can measure BAO from it. We can measure the sound horizon from it. This plot shows the distribution of galaxies from Sloan telescope project, the one we need to plug in the fibers by hand. So far, it provides the largest data set. So how to measure BAO, or sound horizon, from galaxy data? As I say, this sound horizon is imprinted statistic in the distribution of galaxies. So what we do is to measure the separation of the pairs of the galaxies. We will find that the galaxies prefer to be separate from each other with the distance of BAO, or sound horizon. In this plot, the x-axis here is the separation of the galaxies, and the y-axis is the number of the pair correspond to that separation. So here, the first band here is showing that the galaxies intend to be closer to each other because the gravity. So galaxies are trying to pull each other together, so you have more pairs at this region, this separation. However, there is an additional bump here. It means that galaxies also prefer to be separated from each other with this spatial distance. We know this spatial distance corresponds to the sound horizon, which is around 450 million light years. This feature was there even before the galaxies were formed. It's not like galaxies try to modify their, adjust their separation to have this separation. It's actually, it was there before the galaxy was formed. Okay, now if we can put all these sound horizon measurement, all these BAO measurement together, including the one we measure from the cosmic microwave background at the time that the sound stopped, and the one we measure from galaxy data, we can reconstruct the expansion history of our universe. DESI, which use 5,000 robots to move the fibers, will provide many more data. In this plot, I'm comparing the one from Sloan Digital Sky Survey on the top and the forecast from DESI on the bottom. As you can see, DESI data is much denser, so that we expect that to have much more precise measurement. Given the dark energy is basically the biggest problem that we are trying to understand using this new data, we put dark energy in the name of the survey. That is why we name it Dark Energy Spectroscopic Instrument, DESI. Okay, as a summary, I have introduced you Sloan Digital Sky Survey and DESI Dark Energy Spectroscopic Telescope project. We talk about supernova 1A and understand why we can use it as a standard candle and to measure the expansion of our universe, and then how we find out a dark energy problem, which turns out get a Nobel Prize in 2011. We also talk about BAO, the sound horizon, and we also talk about cosmic microwave background, the signal from the time at the sound stop. And in the future, DESI is collecting the detailed colors of galaxies, 5,000 at a time, to build the largest precise 4D structure of our universe. So we are now in a better position to solve one of the biggest problems in cosmology, dark energy. Okay, I think that's all for today. Here I put the links for the video I showed today in case you want to see them again with higher quality. Thank you for listening. I hope you enjoyed the talk. I'm happy to answer some questions.
Okay, well, thank you so much, Albert, for that fascinating talk. I don't know about everyone else, but I find it absolutely amazing that you're able to build those plates that carry 5,000 fiber optics, 5,000 eyes, all looking at different galaxies at the same time. And you're able to separate the light from those galaxies into the different colors, which translates that two-dimensional image of the sky into this three-dimensional map that goes back through our universe, even looking back in time. So we've got a few questions that have come in from our audience. Just a reminder for everyone, if you want to ask questions, if you're joining us over on YouTube, you can put your questions in the chat, or if you're with us on Zoom, you can head down to the bottom of the screen and click the Q&A button, and you can send in your questions there. So thinking about those plates that hold the optical fibers, how precisely do those plates need to be made in order to make sure those fibers end up in exactly the right position?
Okay, that's a great and very technical question. I'm sorry, I don't have the answer for that.
Sure, no problem. I guess we always make sure we hire some very skilled engineers that can solve these problems for us and build us the technology that we need. So I wonder if you could tell us then, each of these plates, it must have holes specifically drilled for each position on the sky. So you have to have a hole for each galaxy. Are these plates single use, or do you use them again and again to observe the same patch of the sky?
It's for single use. So actually, in the end, there are so many plates, and the project distributes all these plates to different university, and then it's become a very fine art in the different departments.
Sure. Okay, and you talked about how we use supernovae to measure the expansion of the universe, to find the distance to these galaxies. So supernovae are explosions that go off suddenly at the ends of lives of massive stars, or when a white dwarf star gets a little bit too big. So how long can you see a supernova for after it explodes? Do you need to observe it very quickly after it goes off in order to be able to use it to measure the expansion of the universe, or do you have a little bit of time?
Yeah, I think I'm not expert of supernova, but as I know, this light curve would drop in days or weeks.
Okay, so you don't have to be right there and then. You've got a few days or weeks to go and look at it and get the measurements. Great. And you showed that famous pie chart that shows how the normal matter that we're familiar with, so the stuff that makes us, the stuff that makes the stars, the planets, and just about everything we're used to around us, it makes up only 5% of the contents of our universe. Another 25% is this mysterious dark matter, and a whopping 70% is dark energy. So one question we had come in, when you show dark energy, this mysterious force, if you like, that's causing the universe to expand and to accelerate, when you show it on that pie chart, does this mean you are able to consider dark energy as being a physical entity in the same way that we think of matter and dark matter?
Entity. Actually, I'm not sure what that means.
Oh, so can we think of it as an object in the same way that we can assign a mass to it, or in the same way that how do we compare the dark energy to the amount of matter?
Okay. I'm trying to think that whether there's an easy way to answer these questions. So because in the gravity theory, I mean general relativity, we do have the energy turn that would determine how the universe evolve, how the size of universe evolve. And it turns out that we need to put something, okay, it has positive energy. Of course, basically all the, we consider all the element with has positive energy, but it has negative pressure. This is a spatial thing. I mean, it's dark, even dark matter or no matter, they are also all have positive pressure, but we need to put something that's very weird. It has negative pressure, and then in the end, it will increase the expansion rate of the universe.
Yeah, sure. So it's sort of so you were almost saying, so we know from Einstein's theory of relativity that explains to us how gravity works and how ultimately how the universe expands based on what's in it. We're essentially treating the dark energy in the same way that we treat the matter. So we know how much gravity that the matter produces. So then we can assign an equivalent value to the dark energy that's counterbalancing it.
Yeah,
I guess. So one question, just to sort of dig deeper into exactly how dark energy works and how the universe expands. Does the fact that the universe is accelerating mean that the amount of dark energy is increasing, or can the dark energy be constant and produce an accelerating universe?
It's in terms of the fraction of dark energy, it is increasing, but it also depends on what is dark energy anyway, because dark energy could be just a constant in the Einstein equation, and this constant actually people and some people do not like it because it looks ugly when we add a constant in a beautiful Einstein equation. So in terms of energy, I'm not sure whether the energy is increasing if you consider it is additional element. Sorry, I'm not sure about that.
But I guess you could also have an expanding universe that is accelerating even if the dark energy is constant. I guess you could think of it in sort of the same way as a force pushing a cart or something. A constant force on a cart will cause the cart to accelerate in the same way that you could have constant dark energy accelerating the universe, or you could have dark energy that's changing in time.
Yeah.
So related to that, the measurements you make with DESI, will they be able to tell us if dark energy does change in time or if it was the same over the history of the universe? Is that something that DESI can measure?
That's the hope, because DESI actually has much better precision that we can reconstruct the evolution of the size of the universe. So we can really track down how this accelerated through time. So that's the hope that we can really tell whether we can rule out some model in this case.
And thinking about the Baryon acoustic oscillations you talked about, the sound waves that were propagating in the early universe, you said that they give us a constant size scale, almost like putting rulers across the universe. So that separation of 450 million light years, I think you said, is that constant throughout the history of the universe, or does that was it smaller in a younger universe?
So it depend on how you look at it. Right. So if consider, say the size, okay, the universe has many galaxies, and then the separation of the galaxies, if you consider that is fixed, and then it's just the universe expanding. Okay, so that's basically how we consider that is the standard ruler. If you consider two galaxies, they are not moving away from each other. You consider they are actually with fixed this separation, and then the universe expanding. Then the sound horizon is fixed. So we kind of play with this coordinate, this to define this sound horizon.
Yeah, and is that because in the early universe, those sound waves, when they could travel, were moving out, and then they managed to travel 450 million light years, and that's the point they got frozen. So they expand out at the beginning, and then after the recombination event that stops the sound waves, then the waves stop. So after that point, then they're frozen in time. Is that right?
Right. But the space, it could still expand. The whole universe is still expand. So when we look at it, we still see the size of the sound horizon get bigger.
Yeah, and that's really useful because it's almost like somebody went laying rulers all the way across the universe that then we can go and look at, even though those rulers have moved apart.
Right, exactly.
We can still use them to measure things. Right. Okay, so I think we've just got time for one more question before we wrap up. I was wondering if you could tell us, Albert, thinking about the next 10 years in astronomy and cosmology, what breakthrough would you say you're looking forward to the most?
Wow, okay. In 10 years, dark energy definitely is the one important problem we want to solve. And the dark matter is another one. And in 10 years, I would hoping that we could really tackle down the dark matter problem, because it could be solved on Earth, not through the space. And for dark energy, we are still looking for more and more data, and then it's hard to see. I would say I can answer that question after we saw the result from DESI.
Great. Well, yeah, and absolutely looking forward to that. And well, thank you so much, Albert, for joining us tonight and sharing your expertise with all of us. And thank you, everyone, for joining us tonight. It's great to be able to share our science and our discoveries with all of you. If you'd like to see tonight's presentation or any of our past presentations again, they're all recorded over on our YouTube channel at youtube.com/kipac. But otherwise, we'll be back in 2 weeks' time on Tuesday, December 1st. You can find out more over on our website, kipac.stanford.edu/discover. You can subscribe to our channel on YouTube, or you can join our mailing list to stay up to date. But goodbye for now, everyone. Stay safe, and we'll see you in 2 weeks.
Thank you.